Hey everyone, welcome back to the Virtual Eclipse Community Meetup. I'm your host, Stephanie Swart, and today I'm joined by software architect and general manager of Eclipse Source, Philip Langer, who will be presenting diagrams in the web and space with GLSP. So without further ado, Philip, over to you.
Thanks a lot, Stephanie. Welcome everyone to this talk about building web-based diagram editors. I'm really thrilled to talk about this topic, especially since we have created a new Eclipse incubation project called Eclipse GLSP, or the Graphical Language Server Platform. Basically, the main idea is to apply the architecture of the language servers and language server protocol also to diagrams, so that we can basically benefit from all the same advantages that also language servers provide for textual languages, but also use them and take advantage of them for diagrams. Before going directly to the specifics and diving into GLSP, I would like to mainly describe a little bit the background or our background and the angle from which we are approaching this topic, because I think it's very important since it shapes a lot the architectural decisions that we took on this way. So basically what we are, our background and what we are mainly doing in most of our projects at Eclipse Source is building domain-specific modeling tools for various domains. And since various domains are involved, of course, also these modeling tools take very different shapes. So often we deal with only information system kind of modeling tools where we have form-based UIs. If it gets more condensed information, we often have also table-based. And this goes more through systems and software engineering tools, where we then are dealing more and more with textual languages through to programming languages, as well as graphical diagrams and graphical languages. Even though they look a lot different, they share one common thing, and that's that they all are based on the Eclipse modeling project, or on technologies that are provided in this project, and that they are built and well integrated with the Eclipse Rich Client platform. And this is really great since it's very, very efficient to build these tools based on those technologies and platforms. And it's amazing how fast you can get a tool, a modeling tool that is really tailored for a specific domain based on those technologies by using one of these representations or even combining them arbitrarily. However, one thing that becomes more and more important is that we also would like to reach a user base that is outside of this Eclipse Rich Client platform tool community. And that's, for instance, integrating modeling tools in existing applications that are not Eclipse-based, or even integrating them in cloud IDEs such as Theia, for instance. And when you would like to do that, then you suddenly realize how great these Eclipse Rich Client platform and Eclipse modeling projects are integrated, because then you feel suddenly how much you have to re-implement to achieve the same. And that's exactly more or less what we have seen also now coming up a lot with textual languages. And here this problem is solved with the language server protocol, where we already can very easily provide the same tool support for rich client applications, but also, for instance, for cloud IDEs such as Theia. In the form-based and table-based UI area, we are also already quite well equipped with a project called JSON Forms, where we can also provide very efficiently modeling editors that use form-based user interaction. However, in the area of diagrams, there is a little bit of a dark spot, so there is no clear technology so far that we can just use directly to build, for instance, web-based diagram editors. And that's not only to reach a larger customer base, but that's really a pity, because web-based diagram editors would provide a lot of benefits. Mainly two benefits are the most important ones. The first is deployment and integration. Because when you, for instance, have a web-based deployment model or a cloud-based deployment model, a browser is all you need, so you don't need to install anything on the user's machines. And you have a really flexible resource allocation. So, for instance, users who do very hard computation stuff can get more resources very easily and dynamically assigned than others, for instance. And this deployment and integration advantage allows you to integrate diagram editors virtually anywhere in any existing application by embedding a browser, or maybe the application is already browser-based and it's even easier. It also gives you more flexibility in terms of avoiding this IDE smell when you're building modeling tools, because when you're building a modeling tool on Eclipse Rich Client platform, it always looks like Eclipse, of course, and Eclipse, of course, looks a little bit like an IDE. And maybe your user base would be better catered if you have a different style of application. So that would also be possible. But the most important fact is that you could include more people in the overall modeling process by being able to integrate certain bits and pieces of a diagram editor, for instance, into existing applications that they are already using today when introducing modeling, for instance. The second main advantage, of course, is modern UI technology. So HTML5, for instance, provides lots of flexibility. There is a lot of innovation going on. New frameworks are coming out, which are making UI development very, very easy. When you compare that to SWT, which is fine, of course, but there is not a lot of innovation going on, and it's sometimes very, very hard to implement certain specific or more advanced features like animations and stuff like that. The same is basically also true for Jeff3 when you compare it, for instance, with SVG, which allows you also quite easily to provide model-looking diagrams. And CSS3 styling, for instance, of course, is also a great plus because you can can achieve very flexible diagram styling. And as I mentioned before, things like visual feedbacks, animations, and stuff like that are very easy to implement. There is, of course, however, as I mentioned before, one big disadvantage for web-based diagram editors, and that's frameworks. Because if you compare the existing ones from GMF, for instance, Sirius, Papyrus, and so on in the Eclipse ecosystem, with what we have in web-based technologies, then, of course, you immediately feel the difference. So there are a couple of frameworks available, so that's for sure. There are a few client-side diagramming libraries that you could use. So for instance, Joint.js or the commercial version Rapid or MXGraph and so on. And we built a few diagram editors based on those technologies, and we actually had pretty good experiences in doing so, especially with Joint.js. However, these frameworks are client-side frameworks, so they only address a small piece in this whole puzzle that you, when you want to build a modeling tool based on browser technologies. So what we actually need would be sort of a flexible client-server architecture to address all these requirements. And the reason why a client-server architecture is so important to us is because in our use cases that we have when building commercial or open source engineering tools, which are often very complex, which involve multiple large models and editors that interact with them, we almost always have the case that one model is not one diagram, but the reality is that there are a couple of editors or diagrams which represent different parts of a larger model. Because the model usually is so large that you can't even put it into one diagram. So you cope with it by having very specific diagrams for certain aspects. But still, that means that that doesn't mean that they are completely separated, but they interact or represent different parts of an entire model. And since we can't load the full model into the browser, we need a mechanism that avoids preventing the model to be loaded fully in the browser, but really just having the diagrams and what really is necessary in the browser, and that's the diagrams to be rendered instead of loading the full model. However, at the same time, even if we would only load a small part of the model into the browser, we need a whole model understanding, because this is sort of required to provide a good user experience. And what I mean with that is that, for instance, when you have two diagrams open in your browser, let's say with this one and this one, and in one diagram you change, for instance, this node and rename it, then you of course want this other diagram to be updated immediately. So basically what the server or the entire model needs to know is which diagrams represent which parts and how they interact with each other and what are the connections. The same is also, of course, true for validation. So for instance, when you change one diagram, then only the knowledge of this diagram is not enough to present feedback to the user whether a certain change of the diagram is currently valid or whether there are errors in the models caused by this change. And that means, of course, you need to have a full understanding of the whole model. So what we really need is a sort of a client-server concept where the client represents and renders the diagram, but the server encapsulates the knowledge about the whole model and the modeling language. Very often also a use case is that the modeling language know-how or implementation already exists. There are hundreds of editors and modeling languages already implemented, and we can't really re-implement all of them from scratch, so we would like to reuse them. However, those implementations usually are Java-based, based on EMF, for instance, in the Eclipse modeling framework, and we, in order to avoid having to re-implement them, but still take advantage of them in browser-based applications, we need to put them on a server and have some way of interacting with the diagrams which are rendered in the browser. And the more we thought about this issue and the more we faced it in different projects, we realized that this is actually the same problem that's already addressed with the language server protocol and textual languages. Because when you consider, for instance, a Java file that you have opened in one editor, this Java file could get, for instance, syntax errors because you change another Java file, for instance, the superclass. You remove a method, and this the editor shows the method that you have overwritten from this other class. Then suddenly there should be a validation error in your one editor, even though another editor has changed. So there is essentially the same problem that the server needs to have an overall language understanding, but the client is very thin and only understands what it needs to show. And basically, here with when we saw this parallel requirements or these parallel issues, we identified the requirements that we need something like the language server protocol and language server architecture, but for diagrams and modeling in general. And that's exactly what the project, the Eclipse Graphical Language Server Platform, is about. It's basically applying the architectural pattern of LSP to graphical modeling. And with that, we would like to enable, on the one hand side, the development of web-based diagram editors, or basically clients in any technology, by decoupling the client implementation, so the rendering of the diagram, from the modeling language implementation. And the modeling language implementation encapsulates basically all the editing behavior, the rules of how to change a model, what is allowed, what is disallowed, and so on the server side. With that, we can also, of course, then more easily reuse existing implementations. So for instance, existing implementation of a UML editor by deploying this part on the server and only replace the rendering with a client part. And the client part should really be front-end focused and should only consider rendering and user interaction aspects, but shouldn't be aware of actually the editing behavior. So basically everything that goes beyond rendering and user interaction should be obtained from the server with a minimum amount of round trips, of course. So we don't want to have too many round trips that may cause scalability issues. And basically that's what we want to achieve. One thing that we found in thinking about this graphical language server platform is another project which is called Eclipse Sprotty, also in the Eclipse Foundation. And Eclipse Sprotty is basically an SVG diagram framework written in TypeScript that perfectly fits the requirements of implementing a client-side diagram rendering. So for the client part, we reuse Sprotty a lot. And the reason is because it has a really great and extensible architecture. So it's very slim abstractions. It's based on dependency injection. So if you, for instance, know Xtext, the style of implementing Xtext languages, it's also based on dependency injection. It's very, very similar. And that makes it really flexible to be used. And it's truly open source because it's part of a great open source foundation, that is the Eclipse Foundation. So it's very easy and very convenient to collaborate on this project by contributing things and being part of the community. And Eclipse Sprotty, for instance, here there are two diagrams that have been built with Eclipse Sprotty. Since they are based on SVG and CSS, you have a lot of flexibility in providing different visualizations and rendering techniques. One other thing that is worth highlighting about Eclipse Sprotty is that it's integrated with Xtext and the language server protocol implementation of Xtext. And how that works is basically that Sprotty and language servers allow you to visualize a model or a textual Xtext-based file in some diagram. That's basically the use case that Sprotty would like to achieve with this integration with the language server protocol. So you can consider you have a textual model on the one hand side, and you want to have a visualization of certain aspects of this model. Then Sprotty allows you to build these visualizations by attaching it to the language server that is driving basically this textual model. And with that, of course, Sprotty already has a client-server protocol because, of course, this textual editor communicates, or here is a better picture probably, textual editor communicates with a language server by editing here certain lines and characters, for instance. The language server extension of Sprotty can then be attached to this language server and can send back down to the Sprotty client a representation of this visualization. And when you, for instance, change something here in the textual client going this way, the Sprotty client can be updated and re-render, for instance, the diagram. So here we see that we have already a client-server protocol that is already very, very well suited for diagram transfer and stuff like that. And we already have here the fact that the server manages the whole model, and the client doesn't need to know the entire model, but only what it's showing. And this protocol that they speak is purely oriented towards the front end that is basically showing the diagram. And that's already was a very great start for us that we could take this, not only the rendering technology behind Sprotty, but also the client-server architecture as a base for the Eclipse Graphical Language Server Protocol and platform. So looking at that, what is actually still missing for achieving the goals that we have with the Graphical Language Server platform? Basically, the Sprotty server implementation, as shown also on the picture before, depends on a textual language server. So basically, the textual language server is the master, and it manages the model, and the graphical model is sort of the slave. It just is a read-only visualization of the current model that is actually captured in text. So basically the abstract syntax tree behind the text. What we need sort of in GLSP is to have really an independent diagram server framework that we can build also when there is no textual model alongside it, and there is, with that textual model, no language server managing it. We also, looking at the diagram, looking at the client server protocol, it's also very, very geared towards the viewing and navigation capabilities, of course, because that's their main use case. So what we sort of need to add in terms of GLSP, we need also, of course, things about or messages and protocol about model editing capabilities, like adding nodes, deleting nodes, semantic moves, changing properties, and stuff like that. And last but not least, on the client side, showing the diagram, this is really also mainly targeted towards visualization purposes, read-only visualization purposes. And what we would, of course, need for building real diagram editors is UI for editing and user interactions for editing. So editing tools like a palette, drawing an edge from one node to the other. And with that, our main picture that we would like to achieve, also, if you remember back on the first slide where we had these different modeling tools with different editors like form-based, text-based, graphical, that we can all combine with each other. So then we would like to achieve the same thing here with the language server architecture, basically allowing that you have a server that manages a model that implements also the editing behavior and the rules of the modeling language, and then we can attach different representation-specific language servers to it. So, for instance, a graphical language server, a text-based language server, and maybe a form-based language server that all communicate with the same model and edit different parts of the model, but send them down geared and optimized for a specific type of client. So, for instance, a graphical client, a form-based client, or a textual client. So, no of these clients actually need to understand the full model, but they can still at the same time work on the joint model without knowing everything and need to understand actually what they are doing. So that's really the idea of language servers applied to different representations of models other than text. So, for instance, graphical and form-based. So to address those things that are still missing, the Graphical Language Server platform, of course, reuses a lot of and builds a lot on Sprotty by, for instance, reusing the client implementation, which is great because then we already have a very, very good basis for the rendering of diagrams. And it also uses the Sprotty's client server protocol that I mentioned before for transferring models between the server and the client. What it adds on top, the Graphical Language Server platform adds on top of that is, first of all, a Java-based server framework that allows you to build standalone language servers or diagram servers for particular diagram languages like human class diagrams or eco diagrams or whatever. Second of all, it adds an extension of this base protocol from Sprotty to allow things like invoking the execution of operations of the diagram, creating new elements, for instance. It provides messages to so that the client can be advised about the language configuration. So, for instance, which operations are actually allowed at a certain point, and so on. So that's the protocol part. And finally, the third thing is the web-based client framework. So here, as I mentioned before, for rendering, we directly reuse Sprotty. But on top of that, of course, we need things like connection and interaction to a graphical language server so that actually the client can interact with a graphical language server. Maybe integration with Theia, so it provides a integration with Theia, but it can also be used standalone. And finally, also, of course, UI for editing support and things like, for instance, a palette, tools to create edges and stuff like that, and how these interactions with those tools will then invoke protocol messages sent to the server. So, as I mentioned before, GLSP is an Eclipse incubation project. It's the source code is currently still hosted on GitHub, but is currently in the process of being contributed to the Eclipse repositories. But the project has already been established, so we hope that we can in the next 2 or 3 weeks complete the contribution process. If you want to check it already now, feel free to directly also look it up on GitHub right now. It will be exactly the same code that is currently on this GitHub repository, which is linked down here. Right, so how that was very generic and abstract. Maybe let's look a little bit into how things really work. So looking at one example, how the client-server interaction works, and then I will go straight to a demo. So looking at, for instance, here this interaction chart or this sequence diagram, we have here a user who decides to open a diagram. So it creates a new GLSP client, basically. And as soon as this is created, the GLSP client will start and initialize the graphical language server depending on which file has been opened. We'll select the correct language server and we'll start it off and connect to it. Once this is connected, we use the Sprotty base protocol to obtain the diagram that has been loaded from the graphical language server. So basically, this diagram representation I will show you in a second in the demo is a JSON-based description of the diagram. Once this is sent back to the client will just render it and will then send further messages to the server to learn about what which actions and operations can actually be done. So there is a couple of different things that the client here does. in terms of language configuration, obtaining the language configuration. The first one that it does is, for instance, it requests all the available operations that that the client can actually now perform. So, for instance, these operations can be represented like, or are represented like that. So they all have an ID, they have a label, of course. Then they have an operation kind, which is, for instance, creating a node, creating an edge, deleting something, changing the size or the bounds of something, moving, and so on. And then they provide optionally an element type ID. So descriptions like that, in terms of the available operations, are then sent back to the client. And with this information, the client can then render, for instance, a palette and provide these operations to the user. Once the user would then use, for instance, the palette to execute an operation, the user would invoke, for instance, a node creation. With that, the client would then send a create node operation message to the server, indicating the type ID that it received before from the server, and for instance, the location on the diagram. And then the server can actually receive this message, manipulate the model, send back a model update, and then the client would re-render the diagram to show the result of the operation. So let's have a look at how that actually looks like in a actual editor. So here I have Theia IDE. So just in case you don't know Theia, it's a cloud IDE framework or platform that allows you to build cloud modeling tools, cloud IDEs, or cloud applications. And you can basically create or define, very similar to the Eclipse RCP framework. You can define views. You have things like a menu, file explorer, and so on. And you can define custom editors for a specific file type and stuff like that. It's really a very nice platform to be used. So GLSP is integrated with Theia. So you can then, so we have in this example here, for all files which have an extension of WF, we have registered the GLSP client for a specific example diagram language, which is a very simple workflow example. So as soon as I open it here, you see here that a diagram editor is opened, and this diagram editor shows all the nodes and edges that are represented in this model. You also see that we have here a palette that you can use, for instance, to create a new automatic task or automated task that can be added, for instance, here, and we can start, for instance, drawing an edge between that. So that's all nice. What's really very interesting now is to look what actually happens in the server, because as I mentioned before, when I open the diagram, the first thing to do is that the client would start the server, unless it's already running, and would request the model for the open diagram, for the open file. So I will just go back here to an Eclipse instance where the server is currently running. As you can see here in the console, I will just open up here the console so that we can have a look at it at the same time. Always on top. Let's just go here. Yeah. So now, for instance, when you look at the, sorry, just have to scroll over here. When we see what actually happened in the so far on the server, is that the server received a request model action. It received a requests operation action. With the information of the model, it started to render the diagram. With the result of the request operations, it created the palette so that the user can actually create nodes and edges and stuff like that. When we now, for instance, create another automated task, then you see here the client sent the create node action to the server, and the server actually performed this operation and then sent it back to the client so that the client can re-render the diagram. Right. So the cool thing, or the important thing to see here, is that the client is really only responsible for rendering everything, and the server is actually responsible and controlling the execution of operations and the definition of which operations can actually be executed. And just so that you can see that this is true, I'm here now going to the configuration, the workflow diagram configuration. behind this language server and show you the parts of the things that are here defined. So, and the first method that is here implemented is the get operations method, which exactly defines these operations that are sent to the client. And as you can see here, we define two groups, and then we define a bunch of operations, and then we create a list and send it back to the client. And those operations, they are exactly the ones that are reflected here in the palette. So for instance, if I now remove the merge node, I save again, I have to remove it here as well, and reload here. Takes a few seconds. And as you can see here now, the merge node is gone, and we can only create these 3 nodes anymore. Of course, we can also do something funny, like instead of creating an even though we say we create an automated task, we change the element type that is specified behind this task to a decision node here, for instance. Save again, go back and reload. And when we now create an automated task, then the server would actually create a decision node here instead. So you see basically the server controls everything that the client can really do. Right. Going back to the slides. So now we have seen that how the operations are sent down to the server. How actually are the operations implemented when they have been executed, or when they have to be executed. Of course, they're implemented on the server. So whenever the client sends a create node action to the server, what the server does is it receives via JSON RPC, that's basically the way how they communicate, receives the message, deserializes it, retrieves for the specific client the model state. Then there is an action dispatcher which takes each message and looks up the registered handler for it, and then it invokes the specific handler. So all of these parts are typically generic, but when you create a specific diagram server implementation, you would usually implement the action handlers that actually perform those actions, because of course, create an automated task is specific to your diagram language, so you need to tell the server what's actually to be done when you create an automated task. And that's basically what this action handler would then look like for creating a node. You basically have to implement one method which actually performs this operation, and then just returns it, and this returned node would then be inserted into the server, inserted into the diagram, so that then we can go back and send the model update to the client. Of course, this is a very simple example. There are more sophisticated use cases. So for instance, when you don't want to directly edit a diagram and model in one thing, but very often you have like a separation between a semantic model, which captures the semantic information behind it, and a notation model, which only captures the diagram coordinates and diagram representation information. Then this handler would look a little bit more complex, of course, because then you would, when you create the node, first create the semantic node here, and then you would create the diagram shape for it, and then I would send back to the client. The nice thing here is, since we are using plain Java, we can use EMF, we can use existing language implementations, and that's exactly what is done here. So for instance, here we use an EMF factory to create a specific EMF or eObject instance. And then here we even create an EMF change add command, so that we use an editing domain, an EMF editing domain, to modify those models. I will show you a demo of this EMF-based server in a few minutes. Right. One thing that is very important to us in GLSP in general is that we would like to avoid unnecessary server round trips. And mostly we would like to avoid them on user interactions. So for instance, when you consider that you are creating an edge, and then you hover with the mouse over the diagram, we want to avoid that we have to send a server request when we at each mouse position change, for instance, or when we hover over a specific element. However, we kind of have to let this give the server the final decision whether I can create an edge or not. So this only the server has the knowledge about the language rules. So how we solve that is by introducing a concept of type hints. So basically, besides the operations which can be applied, the client also requests the type hints from the server, and the server sends then back hints, for instance, which node types exist and which node types support which features. So for instance, are they resizable? Can they be deleted? Can they be moved in another element? Or for edges, what are the sources of a specific edge type, and what are potential targets of a specific edge type? And it sends that back to the client. And when then the client would try to initiate creating an edge, then we can only stay on the server, on the client, and interpret those type hints, and then directly decline creating an edge, for instance. Of course, when we do everything correctly, then everything is as before. So the client says, okay, my type hints indicate that this operation is allowed to be executed. So then it would send it to the server, which then performs the operation and send back the update. So let's look at that in the example. I just undo here all my changes, save again, and go back to the diagram, reload. Now we have again the option to create a decision node. So let's look at the type hints, an example for type hint. So for instance, weighted edges are only allowed to be created from decision nodes, but that they are not created to, they're not allowed to be created for normal tasks. So for instance, here, when I now want to create a weighted edge, and I hover over here a task, then it tells me that it's forbidden. But as soon as I hover over another node type that is supported, I can actually create this edge. Of course, the normal edge, which is allowed on these, they would be going through and would be allowed to create that. The way how this is implemented on the server is exactly the same class as we have seen before. Let me just attach that back here. So basically here we see the configuration of the type hints. So for the node types, we just use the default type hints, which are allowed, which allow you to reposition elements, delete them, and resize them. This is also why we can, for instance, here change the size of this decision node. And for the edges, we specify the type IDs of possible sources and possible targets for each element. So for instance, here we specify the type hint for weighted edges, where we say source element type IDs are only decision nodes, and target element type IDs can be manual tasks or automated tasks. So for instance, if I now want to, I've shown you that we can actually create here a normal edge from a task to another task, so from an automated task to a manual task. If I now go here and say we are not allowed to create an edge from what did I remove now? From a manual task, and save here again, go back here and reload, then suddenly the client would disallow me to create an edge here from a manual task, but it will still allow me to create one from automated tasks. So that's our way to sort of avoid having to ask the server on each user interaction, but have sort of a description, a formal definition of what is allowed, and then this definition is sent to the client once and can be reused over time by the client to avoid server interactions. Right. Of course, there will be situations where we cannot cover all cases with this technique. So then other options are, of course, that the server would send back problem markers to indicate that you did something that was actually not allowed. Or finally, the server can also decide to reject actually an operation. And this is actually very easy, because the server would then just send an update of the model without the result of the of the operation, and that's also very easy to demonstrate. So when I open the handler that is responsible for changing the bounds, so changing the coordinates and the size, and I just go back here. Oh, sorry. Whoop. Too many windows, so go back here. So now you can see I can move this node back and forth. When I now go to the server and I just uncomment the line that is actually performing this change, so setting the bound is now just not done. And I go now back to the client and try to move it. You see that the node will always be repositioned to the same position it was before. That's because the server now rejects the operation. Okay. So other things, of course, that are the GLSP is providing, except for the server and the protocol messages that go with it, is the client framework. So a few words about the client framework, just to mention it again. It's based on, for rendering the graph models, it's based on pure Sprotty. So you have all the same flexibilities and possibilities to render diagrams based on Sprotty. So we just reuse that. What we also provide with the GLSP client framework is the GLSP server communication. So basically a TypeScript component that allows you to connect to a standalone GLSP server instance. And it also handles, of course, the dispatching of events locally to the server. Finally, we also provide a Theia integration that you have also seen here. So that's basically the Theia integration that you can reuse, that you can use GLSP very easily in Theia. And then you've seen a lot of them. GLSP provides a couple of Sprotty extensions to enable certain editing capabilities. So you've already seen editing tools like creating nodes and creating edges, the palette, visual feedback tools. For instance, while you create an edge, we draw this intermediate or this edge being currently created. Also, the dirty state handling here is handled by the client in terms of the client asks the server whether a diagram is currently dirty or not. And finally, we have a couple of additional features for editing integrated, such as a command palette, which I will show you in a second, and the direct editing capability of labels. So maybe first a command palette. Wherever you are, you can hit Control Space, and then the server can provide a couple of operations that can be currently executed. So for instance, you can also create a manual task like that. Or you can, for instance, select now push, and then we center on push and select this element. Also, if you select a specific node, the actions can be context specific that are provided here. So it knows the selected element, and you can now say, for instance, create an edge to, I don't know, which one would look good. Yeah, I think brew. And then we would create a new edge automatically. Another thing is the editing tool for labels. So you can hit F2 here and then, for instance, rename this element. Of course, the rename itself is then again performed on the server, but the client needs to provide the UI for that. Right. So that's so far the rough overview of how GLSP works. But of course, there is several things that we can now do with GLSP. And what we have been doing in the last couple of months is exploring different things, whether the architecture holds our requirements when trying different stuff. One thing that we have tried first is that we not only support these very simple use cases where the GLSP server directly interacts with a model and a diagram, but actually interacts with arbitrary model sources. So that's what I also briefly showed before, where we really integrate existing modeling languages that are implemented with EMF, and that can then be integrated with GLSP. There is also an example in GitHub where we actually modify an XMI model element with exactly the same client that you've seen before, but just exchanging the server, we can suddenly edit XMI files and store the diagrams in a separate EMF-based representation without modifying the client, but just with replacing the client server. And the way how that works is that we basically, whenever a change operation arrives, the change operation is implemented by directly modifying the EMF model, for instance. And then out of this EMF model, we generate a new graph model, send the updates back to the client, and then it would render. And this would even allow to attach other clients also to the same model source as shown in the big picture before. I will probably skip the demo because it looks exactly like that, like the current implementation, but the only difference is that it would directly edit this EMF files. But since we're already quite late in the hour and I have a couple of more things that I would like to show, I would just skip that, and please have a look at the GitHub repository where we have the actual implementation of that. Right. What else? One thing that we also investigated is not only reusing existing modeling implementations like EMF-based models, but even going one step further by reusing actually existing editor implementations. And with that, I mean that we really not only reuse just interacting with the model, but taking, for instance, a GMF model or a Papyrus model and Papyrus editor, attaching to a certain runtime behavior of this Papyrus model. So, for instance, what is actually the palette, which elements can be moved, how are elements being set up, and so on, and attaching the GLSP server to such an implementation so that it would enable web-based diagrams for existing editors that are built on rich client technologies such as Papyrus. And actually, it showed that a GLSP can be attached to basically a lot of different servers, such as, for instance, Papyrus. And what we did as a prototype is sort of create a GLSP server that connects to a layer that is above Papyrus editor, and with that allow editing Papyrus models. And I can show you a very short video about that. So on the left-hand side, you see Papyrus. On the right-hand side, you see a browser-based GLSP-based editor. And when we start modifying this model here, you see that the exact changes would show up in the Papyrus editor. So that's, of course, cool. Even resizes and creations and so on would work. But also all the language configurations, such as the palettes, which operations can actually be executed, are obtained from this Papyrus instance. So this really allows us to reuse quite a lot from existing editors without having to re-implement everything from scratch. And that was exactly one of the main goals that we had with GLSP. We did also the same thing for existing real-world modeling environments. So one modeling environment or engineering tool that we've been looking at was Logicat 3. That's basically an engineering tool for programming PLCs, which provides an ICST editing, but also a function block diagram editing tool. And we took that function block editing tool together with the producer of this engineering tool and applied GLSP to it. And basically what you see here is a GLSP implementation that attaches to the implementation of a rich client diagram editor and reuses a lot of functionality. So for instance, which elements can be created, so which functions can be called, which variables are available, and so on, and provide basically the same editing behavior logic, just in a different client, as we can see here within a Theia application. So that basically the conclusion was that GLSP offers really the opportunity for reusing a great deal of existing implementations. And that's sort of also a migration path from existing rich client implementations of a diagram editor to a web-based one. Right. Last but not least, we also wanted to find out whether we can also cater completely different clients. So, for instance, instead of having the Theia-based and web-based client, can we also attach other devices or clients to an existing GLSP server? And what we did here, what we tried is that we took a GLSP server and implemented a specific client that fuels an augmented reality device, so that we can actually have the same functionality that we have currently in a web-based editor, also in an augmented reality space. And it's of course just a prototype, but it shows that we can use this opportunity to explore different ways of reusing the same diagram implementations, even beyond just normal diagram editors, but also in other domains. And I can show you a video of how that works. So let me just open that. So the device, the augmented reality device, is connecting to a GLSP, obtains the server, obtains the diagram and renders it in a three-dimensional space, such as here an office room in Munich. And it allows even things like interacting with the diagram and so on. So we didn't go very far with this prototype. We didn't allow, for instance, editing things, but stuff like selection and so on is even supported, which is kind of nice. Right. Just going back here. Good. I think more or less just in time to have a few minutes left for questions as well. Just a conclusion and outlook. So what we are planning in the next couple of weeks with Eclipse GLSP is that we contribute the source code now to the Eclipse project that has been founded already, which is just a formality to do, but it's being planned for in the next couple of weeks. Functionality-wise, we plan to look into a property view support based on JSON forms. So many modeling tools not only provide diagrams, but you have often a property view where you can then specify all the details about the selected element, for instance. And we want to achieve that or enable that as well with GLSP-based editors. And last but not least, we also want to sort of enhance this edit hint concept a little bit and explore what the best balance is between complexity of edit hints and ease of use. And as well, of course, we want to enhance the editing capabilities of Sprotty in general a little bit more. So for instance, things like, I don't know, for instance, right-click menus are not yet supported and things like that. Right. Just to sum up, what our experiences so far is are with Sprotty. So with Sprotty and GLSP. So first of all, the Sprotty-based client is really was really a great choice for implementing the rendering of the diagram. It is a great SVG framework where you can implement in a very flexible way interactive visualizations. So that is really awesome. Check out this framework. It's great. Also, GLSP, what our experiences from the recent projects we had with GLSP is that it allows for very high reuse of existing diagram implementations. So when you think about migrating or providing a web-based version of an existing editor in parallel, for instance, then GLSP is definitely maybe worth looking at, because it allows you to basically single source a lot of the editing behavior into one existing component and just make it usable for other clients as well. This hard separation between client and server is actually really nice because it is very future-proof. Once you want to change client again or client technology again, you at least have only to worry about the rendering stuff and interpreting the GLSP messages, but you don't have to really do everything from scratch. And this actually opens up many opportunities to explore different devices that you can hook up with a GLSP server, and with that involve much more people in the modeling process or in the engineering process altogether, which is, I think, always a good thing. And last but not least, it's for sure a very young technology. It hasn't been existing for more than 1.5 years, but we have already adopted it in several real-world use cases, and so far our experiences are quite good. Of course, it's not as mature as GMF and feature complete with all different use cases that you can imagine, but depending on your use case, it might already be mature enough to be actually adopted. So, and that's basically also my final question to you. It would be great if you could get in contact with us to tell us about your use cases, about diagram editors that you want to implement for cloud IDEs or for browser-based applications, because we want to learn about the requirements that existing editor implementations have, so that we can equip GLSP with the respective implementations and functionalities. And with that, I thanks a lot for your time, and I would be thrilled to get questions.
Awesome. So thanks, Philip, for a great demo and presentation. And of course, as always, thanks to the community for coming to hang out with us and learn a little bit about GLSP. So it looks like we have one question from Ricardo, and it says, is there some examples or tutorials that he could try to follow to try it out?
Yeah, so for sure, as usual with young open source projects, documentation is not the strong suit. However, there is a quite good example, I would say. So more or less this example that I've showed here is exactly available on the GitHub project that I've linked before. So when you just look into GitHub and search for GLSP or Graphical LSP, then you will find it. And there is an example implementation for this, which is very simple because it directly writes into the graph representation, the JSON-based one. And there is also a second example with exactly the same, but it interacts with an EMF-based model implementation on the server. So you can check out these two examples to find out more.
Awesome. So we don't have any other questions for today. So again, I'd like to thank you, Philip, for presenting, and we will see everyone next time at our next Eclipse virtual meetup. So thanks, everyone.
Thanks a lot. See you soon.